Welcome back to the Explainer. Today, we're unpacking one of the most elegant mathematical tricks that computers use to solve the seemingly impossible. You know, we rarely think about how a software program instantly spits out the answer to a complex equation that would take us hours to even set up, right? Well, spoiler alert, it's not magic. It's actually a brilliant numerical method named after Sir Isaac Newton and Joseph Raphson. So buckle up, because we're going to demystify the Newton-Raphson method together. So let's start with our central problem. High school math formulas are great for basic quadratics. Sure, you just plug the numbers into that trusty formula and boom, you get your answer. But what happens when we step out of the classroom and into real-world physics or engineering? We start facing these complex, nonlinear equations, things like x to the fourth power equals 5, or crazy equations combining exponential and logarithmic functions. Analytical math just totally hits a dead end here. There's literally no simple formula to just plug your numbers into.
Okay, let's dive into this. If we visualize the curve of one of these equations, there's a specific point sitting right there on the x-axis. That is the mysterious, elusive root we are trying to find. Solving an equation fundamentally just means finding where the function equals 0, where the curve actually crosses that horizontal line. And when analytical math hits a dead end, when we can't solve for that exact point with an equation, we have to rely on computational methods to hunt it down for us.
Section 1. Setting the stage. The search strategy. To actually track down that elusive root, numerical methods generally fall into two camps: bracketing methods and open methods. Think of bracketing methods as the slow, play-it-safe approach. You pick two guesses that physically trap the root between them, and you just slowly narrow that trap until you find it. It's safe, it always works, but man, it takes its time. Open methods, on the other hand, they are the fast, risky thrill seekers of the math world. They only need a single starting guess. They don't trap the root at all, which means, yeah, they can sometimes spiral totally out of control. But when these open methods do work, they converge on the true root incredibly fast. Section 2. The Newton-Raphson idea. Visualizing the magic. Now, our mathematical hero here, the absolute star of these open methods, is the Newton-Raphson method. Instead of trapping a root, it cleverly uses the geometry of the curve itself. And this brilliantly illustrates the whole concept. Imagine bouncing along the curve. We make an initial guess, we go straight down to the curve to see where we're at, and then we draw a tangent line right there, using the slope or the derivative of the curve. We literally just slide down that straight tangent line until we hit the x-axis. That crossing point, that becomes our new, much better guess. It's like we're using a series of straight lines to map out a really complex curve. Let's walk through that physical action in 4 super simple steps. Step 1, make a reasonable starting guess. Step 2, find the tangent line to the curve right at that guess. Step 3, follow that tangent line down to find exactly where it crosses the x-axis. And step 4, repeat. Just repeat the process using this brand new point. The big takeaway here is that computer math isn't some incomprehensible wizardry. It's quite often just highly educated guessing, performed over and over again at lightning speed.
Section 3. Concept to code. The iteration formula.
So we need to translate that simple visual bouncing into an actual mathematical formula so a computer can handle it. Here's how that looks. Our new guess is simply our old guess minus the function's value divided by its slope. That's it. This beautiful, straightforward little formula is derived directly from a first-order Taylor expansion, which honestly completely bypasses any of that major math anxiety. You just punch in your current guess, the function, and the derivative, and the formula spits out a brand new guess that's instantly closer to the true root. Now, you might be wondering, how fast is this? Well, when you have a good starting guess, the error drops exponentially. It's wild. The error at the next step is actually proportional to the square of your current error. So if your error is 0.1, the next step it plummets to 0.01, then 0.0001. It's incredibly fast, but there's a catch. If you make a really bad initial guess, like say starting at -10 for a root that's sitting way over near 0.5, the curve slope might be so shallow out there that the computer has to work 3 times as hard, crunching through 13 iterations just to cross the finish line, compared to solving it in just 4 if we had simply guessed 0. Section 4. Pitfalls and fatal flaws. Remember how we said these open methods are thrill seekers? Well, because the method relies entirely on the slope of the curve, sometimes our hero algorithm fails spectacularly. Now, what's really interesting about this is seeing exactly how it breaks down.
Sometimes an inflection point sends the tangent line shooting way off in the wrong direction. Or the algorithm gets trapped in a valley, just endlessly bouncing back and forth around a local minimum. Sometimes it even accidentally jumps to a completely different route. But the absolute fatal flaw, hitting a zero derivative. If your guess happens to land exactly at a minimum or maximum, where the slope is totally flat, it's like hitting a mathematical brick wall. The tangent line is perfectly horizontal, which means it will literally never cross the x-axis, and your next guess gets shot straight out to infinity. Obviously, we can't have our engineering software crashing every time it encounters a flat curve. So engineers have developed some pretty clever safety nets. To keep the algorithm in check, you absolutely have to code in a maximum iteration loop, just so your computer doesn't get stuck spinning its wheels in an infinite loop forever. You can also set it up to output warnings if a guess shoots out too far, or even better, you use a hybrid approach. This is what powerhouse software like Matlab actually uses under the hood. They use the slow, safe bracketing method just to get close to the root, and then boom, they unleash the lightning-fast Newton-Raphson method to finish the job.
Section 5. Leveling up. Scaling to multiple dimensions. Let's move to and see how this builds because, in reality, engineers aren't just looking at single 1D curves. They're solving massive, complex systems with multiple interacting variables at once. Think heat conduction across different materials or complex fluid dynamics. To handle this, we introduce the Jacobian matrix. Now don't panic. I know that sounds like a scary new math monster, but I promise it's not. Remember how our 1D formula needed the slope, or that single first derivative? Well, when you have multiple equations and multiple variables, you just have slopes pointing in different directions. The Jacobian matrix is literally just a tidy little grid that holds all of those different directional slopes in one place. It's really just a multidimensional upgrade to our standard derivative slope. And check this out. When we look at the multidimensional formula, the core logic we just learned remains exactly the same. We still have our current guess, our function values, and our slope. We've just swapped out the single numbers with matrices and vectors to solve these impossible 2D or 3D problems. The Jacobian matrix takes the place of our single derivative. The formula essentially sets up a system of linear equations that the computer can easily crunch through at each iteration to find the next set of guesses. It just keeps solving this matrix equation over and over and over until all the variables lock into their true roots simultaneously. You know, it's truly fascinating when you finally pull back the curtain on computation. We tend to think of computers as these absolute perfect calculating machines. But as we've seen today with the Newton-Raphson method, solving the most complex, seemingly impossible nonlinear systems in the world is quite often achieved through nothing more than an elegant, geometrically guided series of rapid-fire guesses. So, I'll leave you with this. If computational power is largely just millions of highly refined guesses updating themselves in real time, what other impossible problems in our universe can we simply guess our way out of? Keep that in mind next time your computer spits out a flawless answer. Keep exploring, keep questioning, and we'll see you in the next explainer.